By the end of the 19th century, physics appeared to be a nearly finished science. Classical physics, developed over more than 2 centuries by figures such as Isaac Newton, James Clerk Maxwell, and Ludwig Boltzmann, had achieved remarkable success. It could explain the motion of planets, the behavior of projectiles, the flow of heat, the nature of sound, and the propagation of light and electromagnetic waves. Many leading physicists believed that the fundamental laws of nature were already known, and that future work would only involve refining measurements to a few more decimal places. This confidence, however, was misleading. Beneath the surface of success, serious contradictions were beginning to appear, contradictions that classical physics could not resolve. These problems collectively formed what is now called the crisis of classical physics. Classical physics was built on several deep assumptions. One of the most important was continuity. Energy, matter, and motion were assumed to change smoothly, not in sudden jumps. Another assumption was determinism. If the initial conditions of a system were known precisely, its future behavior could be predicted exactly. These ideas worked extremely well for everyday objects and large-scale systems. However, as experimental techniques improved, scientists began probing nature at very small scales and very high energies. In these extreme conditions, classical theories started to break down. One major source of crisis came from the study of heat and radiation. Physicists were trying to understand how hot objects emit electromagnetic radiation, a problem known as blackbody radiation. A blackbody is an idealized object that absorbs and emits radiation perfectly. Experiments showed a clear and precise relationship between temperature and the spectrum of emitted light. Classical theories attempted to explain this using known laws of electromagnetism and thermodynamics. While these theories worked at low frequencies, they failed catastrophically at high frequencies. According to classical predictions, a heated object should emit an infinite amount of energy at short wavelengths. This absurd result became known as the ultraviolet catastrophe. Since real objects clearly do not release infinite energy, this failure exposed a deep flaw in classical physics. Another serious challenge came from atomic physics. Classical models treated atoms as miniature solar systems, with electrons orbiting a nucleus like planets around the Sun. According to classical electromagnetism, however, an accelerating charged particle should continuously radiate energy. An electron moving in a circular orbit is accelerating, so it should lose energy and spiral into the nucleus within a fraction of a second. This would make atoms unstable, contradicting the fact that matter is stable and long-lasting. Classical physics had no convincing explanation for why atoms do not collapse. Spectroscopy also revealed troubling evidence. When scientists analyzed the light emitted or absorbed by atoms, they observed sharp, discrete lines at specific frequencies. Classical theory predicted that atoms should emit a continuous range of frequencies, not isolated ones. These discrete spectral lines suggested that something fundamentally discontinuous was happening inside atoms, a concept that classical physics could not accommodate. The behavior of light itself created further tension. In the 19th century, Maxwell's equations had established light as an electromagnetic wave, and wave theory successfully explained reflection, refraction, interference, and diffraction. However, certain experiments hinted that light sometimes behaved like a stream of particles. For example, in interactions between light and matter, energy transfer appeared to occur in localized packets rather than being spread smoothly across a wave. Classical wave theory struggled to explain these observations, but the idea that light might have particle-like properties conflicted with decades of successful wave-based explanations. Thermodynamics and statistical mechanics also contributed to the crisis. While the laws of thermodynamics described heat and energy flow with great accuracy, their deeper meaning raised troubling questions. The second law of thermodynamics, which states that entropy tends to increase, seemed to introduce irreversibility into nature. Classical mechanics, however, is time reversible. The equations work just as well forward or backward in time. Reconciling irreversible macroscopic behavior with reversible microscopic laws proved deeply problematic. This tension suggested that classical mechanics might be incomplete at a fundamental level. Experimental discoveries toward the end of the century further intensified the crisis. In 1897, J. Thomson discovered the electron, revealing that atoms were not indivisible as previously believed. Soon after, experiments involving cathode rays, X-rays, and radioactivity uncovered forms of energy and matter that classical physics had never predicted. Radioactive decay, in particular, appeared spontaneous and unpredictable, challenging the deterministic world view of classical mechanics. Even space and time, long considered absolute and universal, were beginning to show cracks. Attempts to detect the motion of Earth through the hypothetical luminiferous ether, a medium once thought necessary for light waves, consistently failed. The most famous of these experiments, conducted by Michelson and Morley, found no evidence of the ether at all. This result was deeply puzzling, because classical physics assumed that waves required a medium to propagate. The failure to detect the ether raised profound questions about the nature of space, time, and motion. Despite all these problems, many physicists initially believed that the crisis could be resolved within the existing framework. They hoped that better calculations, improved experiments, or small theoretical adjustments would restore consistency. Very few suspected that an entirely new way of thinking about nature was required. The confidence in classical physics was strong, and the idea of abandoning its core principles seemed extreme. Yet, taken together, these failures revealed a pattern. Classical physics worked brilliantly for large objects and everyday conditions, but failed when applied to the microscopic world and extreme regimes. The crisis was not due to a single incorrect equation, but to a deeper mismatch between classical assumptions and the true behavior of nature. Continuity, determinism, and classical notions of waves and particles were no longer sufficient. This crisis set the stage for the revolutionary developments of the early 20th century. Attempts to fix specific problems, such as Blackbody radiation, led to radical ideas like energy quantization. Efforts to understand atomic stability introduced new models that broke away from classical orbits. Investigations into light and motion forced physicists to rethink space, time, and causality. What initially appeared as isolated technical difficulties turned out to be signs of a profound transformation. In retrospect, the crisis of classical physics was not a failure but a turning point. It marked the moment when physics reached the limits of an old world, and began moving toward a deeper, more accurate understanding of reality. Out of this crisis emerged quantum mechanics and relativity, theories that would redefine science, technology, and our view of the universe. At the end of the 19th century, one of the most serious and puzzling problems in physics was the study of Blackbody radiation. This problem played a central role in revealing the limits of classical physics and directly led to the birth of quantum theory. What made blackbody radiation so important was not just its technical difficulty, but the fact that it exposed a deep contradiction between theory and experiment, an unsolved energy problem that classical physics could not overcome. A blackbody is an idealized physical object that absorbs all electromagnetic radiation that falls on it, regardless of wavelength or angle. Because it absorbs perfectly, it is also the most efficient possible emitter of radiation. When a blackbody is heated, it emits electromagnetic radiation in a characteristic pattern that depends only on its temperature, not on its material or shape. This made blackbody radiation an ideal testing ground for fundamental physical theories. By the late 19th century, experimental physicists had measured blackbody spectra with great precision, providing reliable data that demanded a theoretical explanation. Experiments showed that as the temperature of a blackbody increases, the total amount of energy it emits increases, and the peak of the emitted radiation shifts toward shorter wavelengths. At low temperatures, most radiation is in the infrared. At higher temperatures, it moves into the visible range and eventually into the ultraviolet. These observations were summarized in empirical laws such as Wien's displacement law and the Stefan-Boltzmann law, which accurately described how radiation depends on temperature. However, these laws were based on measurements, not on a deeper theoretical understanding. Classical physics attempted to explain blackbody radiation using known principles of electromagnetism and thermodynamics. The prevailing idea was that radiation inside a cavity could be treated as electromagnetic waves reflecting off the walls. These waves were thought to exchange energy continuously with the atoms of the walls, eventually reaching thermal equilibrium. Since classical theory allowed oscillators to take on any amount of energy, energy was assumed to be distributed smoothly across all possible radiation modes. This approach worked well at low frequencies. Lord Rayleigh and James Jeans derived a formula, now known as the Rayleigh-Jeans law, that matched experimental results for long wavelengths. However, when this same formula was extended to higher frequencies, it predicted something physically impossible. According to the theory, the energy emitted at short wavelengths should increase without limit. In other words, a blackbody should radiate infinite energy in the ultraviolet region. This contradiction became known as the ultraviolet catastrophe. The ultraviolet catastrophe was not just a small numerical error. It was a fundamental failure. Infinite energy output violated conservation of energy and contradicted every experimental observation. Real objects do not glow with infinite brightness, nor do they release unlimited energy. The fact that classical theory led inevitably to this absurd result showed that something was deeply wrong with the underlying assumptions. Several physicists tried to fix the problem. Some proposed modifications to classical equations, while others attempted to impose artificial limits on energy. Wilhelm Wien had earlier proposed a formula that matched experimental data at high frequencies, but failed at low frequencies. Rayleigh and Jeans succeeded at low frequencies, but failed at high ones. No single classical formula could correctly describe the entire blackbody spectrum. This inability to unify theory and experiment signaled a serious unsolved energy problem at the heart of physics. The core of the difficulty lay in how classical physics treated energy. According to classical ideas, energy could vary continuously and be divided into arbitrarily small amounts. In the context of blackbody radiation, this meant that higher frequency modes were allowed to carry energy just as freely as lower frequency ones. Since there are infinitely many possible high frequency modes, classical theory naturally led to infinite total energy. The mathematics was consistent, but the physical result was nonsensical. The unsolved nature of the problem troubled physicists deeply. Blackbody radiation was not an obscure phenomenon. It was directly related to everyday experiences such as glowing metal, sunlight, and heat transfer. If classical physics could not explain something so fundamental, its claim to be a complete description of nature was seriously weakened. The breakthrough came in 1900 when Max Planck approached the problem from a new angle. Rather than trying to adjust classical equations, he questioned the assumption of continuous energy exchange. In a bold and reluctant move, Planck proposed that energy could only be emitted or absorbed in discrete units proportional to the frequency of radiation. These units later became known as quanta. By introducing this assumption, Planck derived a new formula that matched experimental data perfectly across all frequencies. Planck's solution resolved the ultraviolet catastrophe immediately. By restricting how energy could be distributed among radiation modes, the theory naturally suppressed high-frequency contributions and produced a finite total energy. The Blackbody spectrum was no longer paradoxical but fully consistent with observation. The unsolved energy problem that had plagued physics for decades suddenly had a clear mathematical solution. What made this moment remarkable is that Planck himself did not initially believe that energy quantization represented physical reality. He viewed it as a mathematical trick, a temporary assumption needed to make the equations work. He hoped that a deeper classical explanation would eventually replace it. However, the success of his formula could not be ignored, and its implications soon became unavoidable. The Blackbody radiation problem marked a turning point in the history of physics. It revealed that classical concepts of energy, continuity, and equilibrium were inadequate at microscopic scales. What began as a technical issue in thermal radiation exposed the need for a completely new framework. Within a few years, Planck's idea would be extended by Einstein, Bohr, and others, leading to the full development of quantum mechanics. In hindsight, Blackbody radiation was not just an isolated puzzle, but a warning sign. It showed that nature does not allow energy to behave in the smooth, unlimited way classical physics assumed. Instead, energy exchange is constrained in fundamental ways that only quantum theory can describe. The unsolved energy problem of Blackbody radiation thus became the doorway through which modern physics entered a new era, forever changing our understanding of matter, energy, and the universe itself. Max Planck's reluctant mathematical solution stands as one of the most profound turning points in the history of science, not because it was proposed with revolutionary intent, but because it was born out of desperation. Planck did not set out to overthrow classical physics or invent a new theory of nature. On the contrary, he was deeply committed to the classical world, and believed firmly in the continuity and determinism of physical laws. His solution to the Blackbody radiation problem was a last resort, a mathematical compromise intended to save classical theory from contradiction. Yet this reluctant step became the foundation of quantum mechanics. By the late 1890s, the Blackbody radiation problem had reached a critical stage. Experimental measurements of radiation emitted by heated objects were precise and reliable, but theoretical explanations failed. Existing formulas worked only in limited regions of the spectrum. Wien's law matched high-frequency data but failed at low frequencies, while the Rayleigh-Jeans law succeeded at low frequencies but led to the ultraviolet catastrophe at high frequencies. Planck was determined to find a universal formula that would fit all experimental results without abandoning classical principles. Planck approached the problem using thermodynamics and statistical reasoning rather than purely electromagnetic theory. He modeled the walls of a Blackbody cavity as containing microscopic oscillators that could emit and absorb electromagnetic radiation. These oscillators were assumed to interact with radiation until thermal equilibrium was reached. At first, Planck treated energy exchange in the traditional classical way, assuming it to be continuous. However, every attempt based on this assumption failed to reproduce the observed spectrum. Faced with this dead end, Planck made what he later described as an act of desperation. Instead of allowing the oscillators to exchange energy in any arbitrary amount, he assumed that their energy could only change in discrete steps. Specifically, he proposed that the energy of each oscillator could take values equal to whole number multiples of a quantity proportional to the radiation's frequency. This proportionality constant, now known as Planck's constant, was introduced solely to make the mathematics work. There was no experimental evidence at the time suggesting that energy itself was quantized. This assumption immediately changed the statistical distribution of energy among oscillators. When Planck applied the methods of statistical mechanics using discrete energy elements instead of continuous ones, he derived a new radiation formula. This formula matched experimental data perfectly across the entire spectrum, from low to high frequencies. Most importantly, it eliminated the ultraviolet catastrophe by naturally limiting the amount of energy available at high frequencies. Despite this success, Planck was deeply uneasy about the meaning of his own result. He did not interpret energy quantization as a fundamental property of nature. Instead, he viewed it as a mathematical device, a convenient fiction that allowed correct predictions. Planck believed that the true laws of physics must be continuous, and that quantization was merely a temporary shortcut. His reluctance reflected his philosophical commitment to classical physics and his discomfort with discontinuity in natural laws. What made Planck's solution especially significant was that it introduced a new constant of nature. Planck's constant had units of action and set a fundamental scale for physical processes. Its extremely small value explained why quantum effects were not noticeable in everyday life. Classical physics appeared to work because Planck's constant is so tiny that quantization becomes negligible at macroscopic scales. This insight, though not fully appreciated at the time, hinted that classical physics was an approximation rather than a complete description. Initially, Planck's work attracted limited attention. Many physicists accepted his formula because it worked but ignored or downplayed the quantization assumption behind it. The focus remained on the empirical success of the equation rather than its conceptual implications. Planck himself encouraged this attitude, emphasizing the formal correctness of his derivation rather than its revolutionary meaning. The deeper significance of Planck's reluctant solution became clear only when others began to take quantization seriously. Albert Einstein, in 1905, extended Planck's idea by proposing that light itself consists of discrete energy packets. This bold interpretation went far beyond Planck's original intent and challenged the wave theory of light. Later, Niels Bohr applied quantization to atomic structure, explaining why atoms emit discrete spectral lines. Each of these developments traced directly back to Planck's initial assumption. In retrospect, Planck's reluctance highlights the human side of scientific revolutions. Major breakthroughs do not always come from radical thinkers seeking change. Sometimes they arise from careful, conservative scientists trying to preserve existing theories. Planck's loyalty to classical physics forced him to confront its limitations honestly, leading him to introduce an idea he personally found troubling. Planck's mathematical solution also demonstrated the power of statistical reasoning in physics. By combining thermodynamics with probability theory and a bold new assumption, he solved a problem that had resisted all previous approaches. This method became central to the development of quantum theory, where probabilities replace certainties and averages replace precise trajectories. The importance of Planck's solution lies not only in what it explained, but in what it revealed. It showed that nature does not allow unlimited freedom in energy exchange. Instead, energy is constrained by fundamental units that cannot be subdivided indefinitely. This realization shattered the classical assumption of continuity and opened the door to a new understanding of physical reality. Although Planck himself did not immediately embrace the quantum interpretation of his work, history has judged his reluctant step as revolutionary. His mathematical compromise marked the moment when classical physics quietly gave way to quantum physics. What began as an attempt to save an old theory ended by transforming science entirely. Planck's reluctant mathematical solution stands as a reminder that progress in physics often begins with doubt, compromise, and the courage to follow the mathematics even when it leads somewhere unexpected. The birth of energy quanta marks one of the most profound shifts in the history of science, fundamentally changing how humanity understands nature at its deepest level. This idea did not emerge suddenly or easily. It was the result of a long struggle to reconcile experimental observations with classical theory, and it challenged assumptions that had dominated physics for centuries. The concept that energy comes in discrete packets, called quanta, was revolutionary because it broke away from the belief that energy flows smoothly and continuously. This transformation reshaped physics, chemistry, and technology in ways that continue to define the modern world. Before the concept of energy quanta, classical physics treated energy as a continuous quantity. Whether in motion, heat, light, or electricity, energy was assumed to be divisible into arbitrarily small parts. This view worked extremely well for macroscopic phenomena and everyday experiences. Engineers, astronomers, and physicists relied on it with great success. However, as experiments began to probe microscopic systems and extreme conditions, this assumption began to fail. The immediate trigger for the birth of energy quanta was the Blackbody radiation problem. Heated objects emit electromagnetic radiation in patterns that depend on temperature. Precise experiments revealed a specific distribution of energy across different wavelengths. Classical physics could explain parts of this distribution, but failed to account for it as a whole. At high frequencies, classical theory predicted infinite energy emission, a result that was not only incorrect but physically impossible. This failure signaled a deep problem in how energy was being understood. In 1900, Max Planck introduced a radical assumption to solve this problem. While analyzing Blackbody radiation, he proposed that energy exchange between matter and radiation does not occur continuously. Instead, it happens in discrete units proportional to the frequency of the radiation. These units were later called energy quanta. Planck did not arrive at this idea because he believed nature was fundamentally discrete. Rather, he introduced it as a mathematical necessity to make theory agree with experiment. Planck's assumption meant that oscillators in the walls of a heated cavity could only absorb or emit energy in fixed amounts. The size of each amount was determined by a new constant of nature, now known as Planck's constant. This constant set the scale of quantization, and explained why quantum effects were not noticeable in everyday life. Because the constant is extremely small, the discrete nature of energy becomes significant only at microscopic scales. At first, the idea of energy quanta was met with skepticism. Many physicists viewed it as a mathematical trick rather than a description of physical reality. Planck himself shared this cautious attitude. He believed that continuous classical laws were still fundamentally correct, and hoped that a deeper explanation would eventually remove the need for quantization. Despite these reservations, the success of Planck's formula could not be denied. It matched experimental data perfectly and resolved the long-standing energy problem. The true birth of energy quanta as a physical concept came a few years later through the work of Albert Einstein. In 1905, Einstein proposed that light itself behaves as if it consists of discrete packets of energy. He used this idea to explain the photoelectric effect, where light striking a metal surface ejects electrons. Classical wave theory predicted that increasing light intensity should increase electron energy, but experiments showed that only the frequency of light mattered. Einstein's explanation, based on energy quanta of light, matched observations precisely. Einstein's work transformed Planck's cautious assumption into a bold physical claim. Energy quanta were no longer just mathematical devices. They were real entities that governed interactions between light and matter. This interpretation was controversial and challenged the wave theory of light, which had been highly successful. Nevertheless, experimental evidence strongly supported Einstein's explanation, gradually forcing the physics community to take energy quanta seriously. The concept of energy quanta soon spread to atomic physics. Niels Bohr applied quantization to the structure of the atom, proposing that electrons can occupy only specific energy levels. When electrons move between these levels, they absorb or emit energy quanta of precise amounts. This model explained the discrete spectral lines observed in atomic spectra, something classical physics had never been able to do. Quantization was no longer an isolated idea, but a unifying principle across multiple phenomena. The birth of energy quanta also had profound philosophical implications. It challenged the classical belief in continuity and determinism. If energy changes in discrete steps, then nature is not infinitely divisible. At microscopic scales, processes occur in jumps rather than smooth transitions. This idea forced physicists to rethink causality, measurement, and the limits of knowledge. It paved the way for a new world, view in which probability and uncertainty play central roles. As the quantum concept developed further, it became clear that energy quanta were not an anomaly but a fundamental feature of reality. They appear in the behavior of electrons, atoms, molecules, and even fields. The idea expanded into the full framework of quantum mechanics, where quantization applies not only to energy, but also to angular momentum and other physical quantities. What makes the birth of energy quanta especially remarkable is how reluctant and gradual it was. It did not arise from a desire to overturn classical physics, but from the need to explain stubborn experimental facts. Planck introduced quantization unwillingly, Einstein defended it courageously, and others expanded it creatively. Together, their efforts revealed a deeper structure of nature hidden beneath classical appearances. Today, the concept of energy quanta underlies nearly every modern technology, from lasers and semiconductors to medical imaging and quantum computing. It has reshaped chemistry, materials science, and cosmology. What began as a small mathematical assumption in a radiation problem became one of the most powerful ideas in science. The birth of energy quanta represents the moment when physics crossed a threshold. It marked the transition from a classical world of smooth continuity to a quantum world of discrete structure. This shift did not merely solve a technical problem. It transformed our understanding of reality itself. Max Planck, one of the greatest physicists of the late 19th and early 20th centuries, is often remembered as the reluctant father of quantum theory. While history celebrates him for introducing the revolutionary idea of energy quanta, it is equally fascinating that Planck himself initially doubted the very concept that would transform physics. His skepticism was rooted in his philosophical and scientific world-view, his deep respect for classical physics, and the extraordinary conservatism that characterized his approach to solving Blackbody radiation problem. Understanding why Planck doubted the idea of quantization illuminates not only the human aspect of scientific discovery, but also the revolutionary nature of quantum mechanics itself. Planck was trained and educated in the classical physics tradition. Classical physics, established over centuries by giants like Newton, Maxwell, and Boltzmann, had achieved extraordinary success in describing nature. It rested on several fundamental assumptions. Energy is continuous and can take any value. The laws of physics are deterministic, and processes in nature unfold smoothly and predictably. Planck admired the elegance and universality of these principles. He considered the physical universe orderly, rational, and governed by continuous laws. This classical world-view shaped his intuition and expectations about what physics should look like. By the end of the 19th century, classical physics had begun to encounter serious challenges, particularly in the study of blackbody radiation. Heated objects emit electromagnetic radiation in patterns that depend on their temperature. Experiments revealed that the radiation spectrum had a distinct shape that classical theory could not fully explain. Classical formulas either matched low-frequency radiation or high-frequency radiation, but no formula could capture the entire spectrum. In particular, classical theory predicted that energy emission at short wavelengths should diverge to infinity, a catastrophic failure known as the ultraviolet catastrophe. Planck approached this problem as a conservative physicist seeking to preserve classical principles rather than as a revolutionary seeking to overthrow them. He initially attempted to derive a formula for blackbody radiation using standard thermodynamics and electromagnetism, assuming energy was continuous. Every attempt failed. Faced with persistent disagreement between theory and experiment, Planck made what he later described as an act of desperation. He assumed that energy could only be emitted or absorbed in discrete amounts proportional to the frequency of radiation. These discrete units became known as energy quanta, and the proportionality constant he introduced is now called Planck's constant. Despite the success of his formula, Planck did not initially accept it as a literal description of nature. He saw quantization as a formal mathematical device, a trick that allowed him to reconcile theory with experiment. In his own words, he treated the assumption of energy elements as a convenient hypothesis, not as a fundamental truth. Planck believed that the real laws of nature must be continuous, and he hoped that a deeper explanation grounded in classical physics would eventually render the quantization assumption unnecessary. Planck's doubts were philosophical as much as scientific. The idea of energy quanta violated the core principles he had spent his life defending. If energy were truly discrete, continuity would be abandoned. If continuity were abandoned, classical mechanics might be fundamentally flawed. Determinism, too, came into question. If energy exchanges occur in discrete jumps, nature behaves in ways that classical laws cannot predict smoothly. Accepting quantization implied that nature was inherently granular at microscopic scales, a notion that seemed strange and unsettling to a physicist devoted to classical order. Another reason for Planck's skepticism was that the quantization idea appeared to him as highly counterintuitive. Energy quanta were not just small corrections to classical laws. They introduced an entirely new framework for understanding how matter and radiation interact. Unlike classical mechanics, which could be visualized and described with smooth curves and continuous functions, quantization implied that processes at microscopic scales occurred in sudden jumps. This clashed with everyday experience, where energy appears to flow smoothly, and reinforced Planck's instinctive doubt. Planck also had a cautious personality and a conservative approach to science. He was not the type of physicist who embraced radical ideas without substantial evidence. Even when faced with compelling experimental results, he preferred incremental explanations that preserved existing theory. This temperament explains why, although he introduced energy quanta in 1900, he continued to treat the concept as provisional for years afterward. He did not foresee that quantization would grow into a comprehensive framework capable of explaining atomic structure, light-matter interaction, and the very foundation of quantum mechanics. Furthermore, Planck's doubt reflected a broader scientific context. The physics community of the time was overwhelmingly classical. Ideas of discrete energy levels, probabilistic events, and non-continuous processes were largely unheard of or considered speculative. Even other brilliant scientists were initially reluctant to accept such notions. Planck's hesitation was consistent with the prevailing norms of scientific reasoning. A new theory should build upon, not contradict, well-established principles unless there is overwhelming evidence. He introduced quantization because the mathematics demanded it, not because he was convinced by any physical intuition. Despite his doubts, Planck's work had unintended consequences. While he treated energy quanta as a formal tool, other physicists recognized their deeper significance. Albert Einstein, in 1905, applied the idea to light itself, proposing that electromagnetic radiation consists of discrete photons. Niels Bohr used quantization to explain atomic structure, and Werner Heisenberg, Erwin Schrödinger, and others eventually built a fully quantum mechanical framework. Each of these breakthroughs traced back to Planck's reluctant assumption. In retrospect, his initial doubts highlight a profound irony. A conservative, cautious idea introduced reluctantly became the cornerstone of a revolutionary scientific paradigm. Planck's skepticism also underscores the human dimension of scientific discovery. Scientists, like anyone else, are influenced by personal biases, philosophical commitments, and aesthetic preferences. Revolutionary ideas rarely emerge fully formed in the minds of their discoverers. In Planck's case, the tension between his commitment to classical physics and the empirical demands of blackbody radiation produced a hesitant step into uncharted territory. The reluctant nature of this step illustrates that scientific progress often begins with compromise, doubt, and the cautious testing of new hypotheses. Finally, Planck's doubts serve as a reminder of the distinction between mathematical formalism and physical interpretation. He derived a formula that perfectly described the data, yet hesitated to ascribe physical reality to the underlying assumption. This distinction remains relevant in modern science, where theoretical predictions may precede understanding of their fundamental meaning. Planck's caution ensured that quantum theory emerged gradually, giving the scientific community time to absorb its radical implications and develop the experimental evidence needed to support it. In conclusion, Max Planck doubted the idea of energy quanta because it contradicted his philosophical commitment to classical continuity, challenged deterministic principles, defied intuition, and represented a radical departure from accepted scientific norms. His skepticism reflected both his personal temperament and the broader scientific context of the time. Yet, despite his doubts, Planck's reluctant introduction of energy quanta provided the critical breakthrough that solved the Blackbody radiation problem and laid the groundwork for quantum mechanics. His story demonstrates that scientific revolutions can begin with hesitation, caution, and even reluctance, and that sometimes the most profound discoveries emerge from ideas that their own creators are hesitant to embrace fully. The introduction of energy quanta by Max Planck in 1900 was a revolutionary step in physics, but Planck himself was hesitant to ascribe physical reality to the concept. While he treated quantization as a formal mathematical device, other scientists quickly recognized its potential to explain phenomena that classical physics could not. Over the next decades, a series of remarkable developments expanded and generalized Planck's original idea, ultimately giving birth to the full framework of quantum mechanics. The story of how others expanded Planck's concept illustrates the collaborative, cumulative, and sometimes unexpected nature of scientific progress. The first major expansion of Planck's concept came from Albert Einstein in 1905. At that time, Einstein was studying the photoelectric effect, a phenomenon in which light shining on a metal surface ejects electrons. Classical wave theory predicted that the energy of ejected electrons should depend on the intensity of light, and that low-frequency light, if sufficiently intense, should also release electrons. Experiments, however, showed a different pattern. Electrons were ejected only if the light's frequency exceeded a certain threshold, regardless of intensity. Einstein proposed that light itself is quantized into discrete packets of energy, which he called light quanta, or photons. Each photon carries energy proportional to its frequency. Directly applying Planck's formula beyond the original context of Blackbody radiation, Einstein's bold interpretation was a profound leap. It suggested that energy quantization is not merely a property of oscillators in a cavity, but a fundamental characteristic of light itself. This idea directly challenged the well-established wave theory of light and extended Planck's concept into a new domain. Einstein's photon hypothesis resolved the photoelectric effect perfectly, providing a simple explanation for experimental observations that had puzzled physicists for years. By showing that light energy is carried in discrete units, Einstein demonstrated that Planck's quanta were not just a mathematical trick. They were a real feature of nature. Initially controversial, the concept of photons gradually gained acceptance as experiments continued to confirm its predictions. This marked the first major expansion of Planck's idea, quantization applied to electromagnetic radiation, not just to the energy exchanges of microscopic oscillators. Meanwhile, the implications of Planck's concept for atomic structure began to emerge. Niels Bohr, in 1913, applied quantization to the hydrogen atom. Classical mechanics could not explain why electrons orbiting a nucleus did not spiral inward and collapse, nor why atoms emitted light at discrete frequencies. Bohr's radical idea was to impose quantization on the angular momentum of electrons. He proposed that electrons can occupy only certain discrete orbits, each with a specific energy, and that light is emitted or absorbed when an electron transitions between these levels. In essence, Bohr generalized Planck's idea. Just as energy exchange with oscillators occurs in quanta, so too does the energy of an electron in an atom. Bohr's model successfully explained the spectral lines of hydrogen, providing a striking demonstration of how Planck's concept could solve problems classical physics could not touch. The work of Bohr inspired further generalizations. Arnold Sommerfeld extended Bohr's model by introducing elliptical orbits and relativistic corrections, providing more accurate predictions for more complex atoms. These refinements maintained the core principle of quantization while applying it to a broader range of phenomena. In this way, Planck's original concept grew from a solution to a specific radiation problem into a general framework for understanding atomic structure. Another key development came from the study of specific heat in solids. Classical theory, based on the equipartition theorem, predicted that each atom in a solid should contribute a fixed amount of energy, regardless of temperature. Experiments, however, showed that at low temperatures, the specific heat of solids decreased dramatically, contradicting classical predictions. Einstein, in 1907, applied Planck's quantization concept to the vibrations of atoms in a solid, treating them as quantized oscillators. He assumed that the vibrational energy of each atom could change only in discrete amounts proportional to frequency. This simple idea accurately explained the observed decrease in specific heat at low temperatures, confirming that energy quantization applied not only to radiation and atoms, but also to the microscopic motions of matter itself. Later, Peter Debye generalized Einstein's approach, providing a comprehensive model for solids at all temperatures. In the 1920s, Planck's concept underwent its most radical expansion through the development of quantum mechanics. Scientists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac took the idea of discrete energy and incorporated it into a full mathematical framework capable of describing the behavior of atoms, molecules, and subatomic particles. Heisenberg's matrix mechanics treated energy levels as quantized matrices, describing transitions between states without relying on classical orbits. Schrödinger's wave mechanics described quantization as arising naturally from wave functions, where only certain standing wave patterns correspond to allowed energy levels. Dirac unified these approaches and extended them to include relativistic effects. In all these developments, Planck's original concept of energy quanta remained central. The idea that energy, in certain contexts, cannot vary continuously but must exist in discrete packets, underpins the entire theory. Beyond atomic and molecular systems, Planck's concept was expanded into quantum field theory in the mid-20th century. Here, fields themselves are quantized, and particles like electrons and photons emerge as discrete excitations of these fields. This generalization transformed Planck's quanta from a curiosity in thermal radiation to a universal principle governing the behavior of all fundamental particles. Every particle and every interaction in the universe could be understood in terms of energy quanta, showing how far-reaching Planck's idea had become. Experimental advances continued to validate and extend Planck's concept. Phenomena like the Compton effect, the quantization of angular momentum in atomic and subatomic systems, and the development of quantum statistics for fermions and bosons all relied on fundamental idea of energy quanta. Physicists realized that Planck's constant was not just a numerical factor, but a fundamental scale of nature, setting the size of the smallest meaningful unit of action in the universe. The universality of Planck's constant reinforced the deep significance of his original insight. Planck's concept also inspired new ways of thinking about measurement, probability, and uncertainty. The recognition that energy is quantized led directly to Heisenberg's uncertainty principle, which formalized the limits of simultaneous knowledge of certain physical properties. Quantum mechanics, built upon Planck's initial idea, replaced classical determinism with a probabilistic framework, showing that the universe at its core is discrete, uncertain, and interconnected. In summary, the expansion of Planck's concept was a multi-step, multi-decade process that involved many brilliant minds. Einstein applied it to light, Bohr applied it to atomic structure, Einstein and Debye applied it to solid-state physics, and Heisenberg, Schrödinger, and Dirac developed a comprehensive theory encompassing all quantum phenomena. Planck's humble and reluctant assumption about discrete energy units grew into a central principle of modern physics, demonstrating how a single bold idea, when carefully explored and generalized, can transform our understanding of the universe. The story of how others expanded Planck's concept also highlights the collaborative nature of science. Planck provided the spark, but the full fire of quantum theory was built by many hands. Each physicist who recognized the broader implications of energy, quanta, contributed to a framework that is both conceptually profound and practically indispensable. What began as a mathematical trick to solve a radiation problem became the foundation for understanding matter, light, atoms, and even the fundamental structure of the cosmos. Planck's insight, amplified and generalized by others, forever changed the way humanity perceives reality. The story of quantum mechanics begins in an unexpected, almost accidental way. It was not the result of a deliberate search for a new theory of nature, but rather arose from a series of efforts to resolve specific experimental puzzles that classical physics could not explain. The origins of quantum mechanics can be traced back to the work of Max Planck at the turn of the 20th century, whose introduction of energy quanta to solve the Blackbody radiation problem set off a chain of discoveries that would ultimately transform our understanding of the universe. What makes the birth of quantum mechanics unexpected is that it emerged not from a bold revolutionary vision, but from careful, conservative scientists grappling with stubborn anomalies and reluctant to abandon the classical worldview. At the end of the 19th century, physics appeared complete. Newton's laws of motion, Maxwell's theory of electromagnetism, and thermodynamics had provided a remarkably coherent framework for understanding everything from planetary motion to heat, electricity, and light. Many scientists believed that the fundamental laws of nature were already known, and the remaining work involved refining these laws and making more precise measurements. However, as experimental techniques improved, cracks began to appear in the classical edifice. Observations of Blackbody radiation, the photoelectric effect, and atomic spectra all produced results that defied classical explanations, hinting at deeper principles yet to be discovered. The first unexpected step came in 1900 when Max Planck tackled the problem of Blackbody radiation. Classical theories predicted that heated objects should emit infinite energy at short wavelengths, a result that was obviously incorrect. In a desperate attempt to match theory with experiment, Planck assumed that energy could only be emitted or absorbed in discrete units proportional to frequency. These units, called quanta, were introduced purely as a mathematical device. Planck himself did not believe that energy was actually quantized. He saw the assumption as a temporary trick to save classical physics. Nevertheless, this small and cautious step had monumental consequences. Planck's formula matched experimental results perfectly, eliminating the ultraviolet catastrophe and revealing that energy might not be continuous after all. What makes this beginning unexpected is that Planck was conservative by nature and intended only to patch a failing theory. He was committed to classical physics and reluctant to embrace the radical consequences of quantization. Yet, his work unwittingly planted the seed for a scientific revolution. Others quickly recognized that Planck's quanta could not be dismissed as mere mathematical convenience. Albert Einstein, in 1905, extended the concept to light itself, proposing that electromagnetic radiation consists of discrete packets of energy, later called photons. Einstein used this idea to explain the photoelectric effect, which classical wave theory could not account for. Unlike Planck, Einstein boldly asserted that quanta were real physical entities. This interpretation challenged the centuries-old wave theory of light, signaling the first major departure from classical thought and setting the stage for the broader development of quantum mechanics. The second major expansion occurred in atomic physics. Niels Bohr, in 1913, applied Planck's quantization principle to the hydrogen atom. Classical physics could not explain why electrons orbiting a nucleus remained stable, nor why atoms emitted light in discrete spectral lines. Bohr proposed that electrons occupy only certain allowed energy levels, and that transitions between these levels correspond to the absorption or emission of quanta of energy. This idea successfully explained the observed spectra of hydrogen and other simple atoms. By extending Planck's quantization from oscillators and photons to atomic structure, Bohr provided a coherent framework for phenomena that had long eluded classical theory. Once again, a principle introduced as a solution to a narrow problem expanded unexpectedly into a foundational concept. The unexpected nature of quantum mechanics continued as other scientists explored its implications. Arnold Sommerfeld refined Bohr's model by incorporating elliptical orbits and relativistic corrections, increasing its predictive accuracy. Einstein applied quantization to the vibrational energy of atoms in solids, explaining why the specific heat of materials decreases at low temperatures, a phenomenon classical physics could not describe. These developments demonstrated that the discrete nature of energy was not confined to radiation alone, but was a universal principle affecting all microscopic processes. The real surprise came in the 1920s, when the full framework of quantum mechanics began to emerge. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac independently developed formalisms that extended Planck's initial idea into a complete and consistent theory. Heisenberg's matrix mechanics described systems in terms of quantized energy levels and observable quantities, abandoning the classical notion of definite trajectories. Schrödinger's wave mechanics represented particles as wave functions, where allowed energy states corresponded to standing waves, naturally producing quantization. Dirac later unified these approaches, introducing operators and incorporating relativistic effects. What began as a cautious assumption in a problem about thermal radiation had transformed into a comprehensive, universal theory describing the behavior of all matter and energy. Quantum mechanics also introduced conceptual shifts that were entirely unexpected. Classical determinism gave way to probability. The outcomes of quantum processes could not be predicted with certainty, but only in terms of statistical likelihoods. Continuous energy and motion were replaced by discrete states, and the observer became an essential part of the system in certain interpretations. These radical departures from classical intuition were not part of Planck's original plan, yet they became fundamental to the theory that grew from his initial insight. Experiments continually confirmed the unexpected validity of quantum principles. Phenomena such as the Compton effect, electron diffraction, atomic spectra, and superconductivity all relied on the existence of quantized energy levels. The universality of Planck's constant, which sets the scale for energy quanta, showed that discrete energy is a fundamental feature of nature. From the tiniest subatomic particles to the behavior of macroscopic solids at low temperatures, the quantum world proved real and pervasive, far beyond the narrow application Planck had imagined. One of the most striking aspects of the unexpected beginning of quantum mechanics is how accidental it was. Planck's initial step was cautious, conservative, and motivated by the desire to preserve classical physics rather than to invent a new theory. Yet his act of desperation triggered a cascade of discoveries that no one could have predicted. Einstein's photons, Bohr's quantized atomic orbits, Heisenberg's uncertainty principle, and Schrödinger's wave mechanics all trace back to Planck's reluctant introduction of discrete energy units. The theory grew organically, expanding in scope and depth as successive scientists explored its implications. This unexpected trajectory also highlights the collaborative and cumulative nature of science. No single person predicted quantum mechanics in its entirety. Planck laid the groundwork, Einstein and Bohr expanded it, and later generations of physicists formalized and generalized it. Each contribution built upon the previous ones, often in ways that the original discoverers could not foresee. Quantum mechanics emerged not from a single insight, but from the interplay of theory, experiment, and interpretation over several decades. Finally, the unexpected beginning of quantum mechanics demonstrates the profound influence of empirical observation on scientific theory. Planck, Einstein, Bohr, and others were all motivated by experimental results that classical physics could not explain. Each anomaly, the ultraviolet catastrophe, the photoelectric effect, discrete spectral lines, forced a reconsideration of fundamental assumptions. The resulting theory was not the product of abstract speculation alone, but a direct response to nature's unexpected behavior. In this sense, quantum mechanics exemplifies the iterative process of science. Anomalies challenge existing paradigms, tentative hypotheses are introduced, and over time a new framework emerges that can account for a wider range of phenomena. In conclusion, the birth of quantum mechanics was unexpected in multiple senses. It arose from a conservative attempt to solve a specific problem, not from an effort to create a revolutionary theory. Its implications extended far beyond Planck's original intention, touching light, atoms, solids, and eventually all matter and energy. It introduced conceptual shifts, discreteness, probability, and observer dependence that defied classical intuition. Most importantly, it grew organically, shaped by the insights of many scientists responding to empirical anomalies. What began as a mathematical trick in the study of Blackbody radiation transformed into a universal theory, demonstrating that sometimes the most profound revolutions in science emerge from the most unexpected beginnings.